某个 set 去考虑考。
应该会表演一下。
哦，可以啊。
没有啦，他的 S 的节目应该是非洲凑出来的，所以正常人不会看到。对，他们平常也是凑出来的。
好。
但是我知道，我记得
我也很好奇。
反正真的是送分题，我做这个送分题，下个题你先送。
应该是公文题目啊，不用校训。
不算是吧，我把考期的信息看完了，单元就看完了。
对啊，你看，就是当笔记跟 note， 不是当笔记跟那个影片有落差的时候，
我知道啊，所以我会从 complete space 开始讲。
我太晚知道它落差这么大，我一直以为不知道，我一直以为它只是时间距上落差，但我不知道它的内容差。
跟我看一下。
在录了吗？
我已经把你。
Are we rolling? Okay, we're not rolling.
So, first definition, straightforward. To say like Pn is a sequence and P to infinity. This would means so you want like for n large enough, Pn is close to P. So first write this down. You want for n large enough, the P is small enough. So what's the quantifier here? It would be like, so once for all epsilon, and there exists a number that is big enough. That would be a definition. You want number is big enough that the number here, the point here, is small enough. The distance between the point and the limit is small enough. This definition is like somewhat straightforward from your intuition. There will be some prepositions for converse sequences. The first one, Pn converge, then Pn count it. Why is that? Because like we can choose. You're thinking about like something is converging, right? So you're thinking about something like this. And here's P, everything like is close here. So it seems like most of the point lies in here, and only like finite point in here. So we follow this argument. By definition, there exists some n such that such that n large n So you know Pn, it belongs to one, sorry, P1, Pn. N plus 1 minus P minus 1 plus 1. Right. So it contains this interval here and some finite things. This one is clearly bounded. Hence, this one bounded. Second proposition. Say limits to infinity Pn equals to P, and also limit n Pn equals to P prime, and P equals to P prime. So notice that you cannot do this, right? You cannot do this one's not. This one's wrong. Do you know why this proof is wrong? Like the equal here does not mean equal. It means this line. Does not mean equal, but the notion there. So this argument is wrong because you cannot do this. Like the equal does not mean equal. You don't have this kind of transitivity. So how you prove that? You use that notion to prove it. So you're thinking about if there's P, there's P prime. We're thinking about like if the sequence is you get n large enough, it should be close to P, and it should be close to P prime, and that should not happen if P does not equal to P prime. So we use contradiction. Suppose P does not equal to P prime. Take epsilon equals to this one, and you'll find n1, n2 such that if n is larger than n1, then dp n less than so n larger than n2, then dp p prime pn is less than epsilon. You're thinking about like to make point here and make point here. So just take n equals to maximum, n1, n2, then for n is larger than n, we'll get d p pn from Pn are both less than epsilon, which means that dp p prime is less than 2 epsilon by triangle inequality. triangle equality. This one is dP. These goes in prediction. So a sequence in metric space should only have one limit. And from here, you can now see this one as a number. So after this proposition, this equal means equal. Right. So let me check what's that. R. Should I do? Yeah. So, question 3. If equals a limit point, if it contains a limit point, then there exists a sequence converged to it. And from this proposition, you can see why limit point is a limit point. It is a sequence limit. So again, we use figure to see why it's true. So what we mean by limit point? We mean there's a lot of points near it. So of course you can construct a sequence like this converged to it. So the proof is also straightforward if you see this. So like all n you pick Pn such that dPnP is less than 1/n. And why this is possible? Because P is limit point. And it is easy to see that. So easy to see. We sometimes write this as Pn to P. So we mean this by Pn conversion. Sometimes S and after these, we're gonna see some arithmetic. Arithmetic sequences. One, if we say AN to A, BN to B, then AN plus BN equals to A plus B. Perfect. We're thinking about like to move the intuition. The intuition is like this. We want we'll do this. We want an plus bn minus a plus b. They should less than epsilon. Right. So you'll find that this one is do this an minus a plus bn minus b, and this one is larger. Right. So if you can prove this, and you'll get everything done. They're trying to make this plus this less than epsilon. So what you do, you make this one less than epsilon over 2. Right. So how can done with this one? Proof. Pick. Sorry. For all epsilon 1 can pick n1 n2 if n larger than n1, then an minus a is less than or n2. You'll do this. Hence, for n equals to max n1 n2, an plus bn minus a plus b. This one is less or equal to 2 times epsilon times 2. So you can argument here. So sorry, that's and this one equals epsilon. Done. Minus is similar. I'll just state it. Right. So an, a, b, and b. Yeah.
You just have a negative sequence, right?
I just have a negative sequence.
Define Cn to be negative.
Yeah, but I need
Is that true?
another constant. So I would like to do this again.
No.
So because we now do not have like Cn converts to Ca, but we will have it like soon. A minus b, and reason is an minus bn minus a minus b equal to an minus a plus b minus bn, and it will be the same because this one and this one is the same. So intuition, and I'll not prove it. Just leave it here. 3 an a 6 constants. Then Cn converts to Ca. So how to do this is like straightforward. There's no like further intuition for that. So if c equals to 0, then trivial. Alright, because it will be constant sequence.
So,
Okay.
so the triangle inequality here shouldn't it be minus?
Minus here. AM minus A plus B minus BM. AM minus A plus.
No, I mean the after the inequality, I mean, it should be A minus A minus BM minus B.
Minus BM.
The two absolute values.
You mean this one?
No,
This one?
yeah, that one. No, it's not, you mean it's not minus?
No, it's plus.
Okay.
Like it's from here.
Oh, I see, so because it's plus. No, wait, but it's minus. It's minus there, that's my question.
It's not minus. Why is that
Oh.
minus?
Oh, you flip it to B, oh, okay, I see, yeah. No, never mind, you flip the B minus.
Second. For epsilon larger than 0, you can find n. So the step is similar, such that an minus a larger, lower than c. Absolute. And blah 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 blah. Get it done yourself by yourself. It's the same.
Homework.
Yeah,
This is a
it's-
trivial,
it's-
this is a
it's the
trivial
same thing.
homework question. And then, yeah, because I remember somebody put that in his own textbook, and then after 30 years, he found like, he can't prove that.
I mean, Takutani. Again, okay, cool. So now, I'll skip this part, okay? I'll skip this part, we'll just see. So from now, A is always the limit of A and B is always the limit of B, Bn. So, A and B and A, B. This one is not as single as the previous ones. They're thinking about like, they're trying to make this work, right? But what you have now is two things. One is this one is this one. So you want to try to make these become this, right? So you make transform to this come out. So we'll do this. You're thinking about like, okay, we times B in here. So you're becoming AN, BN minus ABN. So it seems like if we have some ABN here, we can diminish it. So thinking about, okay, times A here. And we have ABN minus AB. So when we plus them together, you'll give us this one. So you write this one is lower than equal to Bn, An minus A plus A, Bn minus B. So it is larger equal to Bn, An minus A plus A, Bn minus B. And this one is convergent. There's no convergence, so this one is bounded. Right. So there should exist some bigger B here, and minus A plus A, B and minus B. And we've done this, and everything will be clear. Alright, so proof. We'll first find this b. Everything reversed. So Bn converges. So we know Bn is less than some b for some b that is big enough. And then for all epsilon, this is peak n1, n2 such that if n is larger than n1, then am minus a is less than 2b of epsilon, and n blah blah blah. Bn minus b is less than 2a epsilon. Or a plus 1 epsilon is 2, like, we do not want to consider the case that a is 0 or a is not 0, just do this one. And everything will be great. Alright. And rest, down paper stuff. Will be exactly the same. This one. If an then so again, we want to do this. So first write this. 1 minus an something like this. Alright. Do you know that it will be less or equal, sorry, it should be equals to an and some a minus an. It will be something like this. You don't want this to be too small. You want this one to be large. You want this one to be small. But this one is like controllable. If you have this kind of feeling that the numerator is more controllable than the denominator. So you want to control this on this one. So you're thinking about like how to make this one large enough. So you put something like close to a, it would be like close to a squared, right? If n is large. It would be something like close to a. So you can find out like here it says some n. That. An minus a is less than 2, something in this one. And we can find, if you pick this kind of n, then this one will be a equals 2 and a minus a. Why? Why? Because you're doing, you now know that this one is equal to this one, right? A minus an. And this one, this guy, because of this one, you know Yes? Cool. Then B, easy for the rest. A over 2 over A minus AN. So goes to A squared over 2, A minus AN. So the proof, we know, like, you know, there exists some n1 such that AN minus A is and for all epsilon larger than 0, we can also pick n2 such that this one AN minus A is lower than 2 minus A squared epsilon. And then take n equals to max and 1 and 2 blah 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 blah. Give me another 5. Take some examples. The first one will be, let's say n plus 2 over 3n. Only converge to. Or this will converge to. It will be straightforward, right? It will be 3. I think a straightforward way to see this is to see it as 1 plus 2 over n and 3. And that is like simple enough to see why it's squared. But like to prove it carefully, this one is enough if you're doing like the course, but in this course we want you to like practice more about the n epsilon or delta epsilon arguments. So we might want to see like something like you pick for epsilon, you pick an n, something like that. And how to do this one? This is the same thing. N plus 2 minus 3n minus 3. What would it be? It would be n plus 2 and negative 6, so it would be negative 6. Right, so it would be the same as you do 6 here. If you're picking this one, is that's then epsilon. If you're picking this one, that's the epsilon. It seems like you need to pick. So you write something like this. That's then epsilon. It seems like you do n plus 2 is larger than 6 over epsilon, and n is larger than 6 over epsilon minus 2. Yeah, sorry, epsilon over 6. Epsilon over 6. Epsilon over 6 minus 2. So that would be enough if you just do this. leave it here to like better understand how it works. Alright. So proof for O epsilon larger than 0, peak n such that if pick n larger than 6 over epsilon minus 2. And you can find that if n larger to n, then n plus 2 over 6, n plus 2 over 3n minus 3 equals to n plus 2 over 6 is less than epsilon over 6 over 6 is equals to epsilon. Something like this. Right. Correct. Actually, I prefer this one. Alright, I prefer this one. Because you don't know, like, once it got minus 2 will be 0 or anything else, but if you do this one, that'll be no problem. And maybe something. How much time do I have? Okay, maybe like 15 minutes. Do that? Yes, I can do that. So if we do something like more complicated. It'll be 9, right? And how we do this, it seems like n squared plus 4n plus 4, 9n squared. So equals to 1 plus n to 4 plus n squared to 4, 9. Alright. We want this one to less than epsilon. So what we want to do is we want 1 plus 4n plus 4n squared. It would be less than, so somehow we want this one to less than this one. We want this one to be small enough to less than this one. Right. And so you will see this one is smaller than this one. Right, so you may want 1 plus n over 8. This one is less than this one. So actually, what you only need is like this one is less than this one. So actually, what you need is, sorry, it would be 9 over epsilon. That's it. Oh. 9 over epsilon. So what you only need is to make this one larger than 70 over epsilon. And the proof would be pick n such that this one, and so this one, and so this one, and so this one, and so this one. But when you are doing this, you're doing reversely. Alright. You don't know why you need this. So you'll see some proof that is doing magic, something like, okay, for epsilon larger than 0, you pick this one. You don't know where this comes from. But what you're thinking about is, you want this to become true, you want this come 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 true. And every step is weaker. So you know you can do it reversely. So what you do is, okay, so we pick this one. And so this one.
There's some question.
You need to minus 9
I need to minus 9.
in.
Oh yeah. You're so correct. You're so correct. You're so correct. Minus 9. Ah, then how do I do this? Let me check. And minus, sorry. Minus 9.
You guys should remind him, like, at the very beginning.
I'm trying.
Minus 9.
You're not loud enough. Yeah, but you should help the team.
Equals to
Even help the professor.
and over 16 minus this one, sorry, 36, 1 plus n minus 4, n squared minus 4. Okay, so now you see this, and you know you want to control on this one. Sorry. That will be more straightforward if we do it this way. So you know that this one is larger or equal to, because this one is huge, so not huge, but it's positive, so you know this one. And you know this one is smaller than this one, so you know that will be n over 72. And you want this to less than epsilon. So you pick n blah 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 blah, so that blah blah blah. No, be okay. You can get it done. Just same procedure. Two more examples. One more example. Two. Oh, 10 minutes. Okay. Okay. P larger than 0, then this one is 1. And why this one is true? You're thinking about, like, you want to control this. Alright, so if you write down something like, so P larger to, we'll first use P larger to 1. That would be simpler. P larger to 1. So you're thinking about, like, okay, I'll write down something like, take, if you say P prime equals to P minus 1, then you're asking about how this would go. How this would go. And I believe that you, actually, I'm not so sure. You learned Bernoulli inequality in the very first class in this course. So you know that this one is less or equal to 1 minus n over P prime. So done. Something like that. And how you do that for epsilon larger than 0, you pick and blah 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 blah, then do it reversely. This one is Bernoulli. Bernoulli. Another interesting example here would be n over n to the 1 over n. So we're thinking about like how to come from this one. Alright, so you may think that, okay, so let us take some one, it may take some 1 plus epsilon to see, sorry, 1 plus k to see how this works. Okay, if it goes like 1 plus k to n, so you're trying to say that k will go to 0 if this one is k. Okay, so if you write down like n equals to 1 plus k, then this one equals to 1 plus nk plus n over n minus 1 over 2k squared plus blah 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 blah. So it can become true to this one, k squared. So it can become true to this one, n minus 1 squared k squared. So again, if you want to this, if you want, you know this one is, it should be larger, equal, okay. So if you know this one is, it should be larger, sorry. If you know this one is larger than n, if you know this one is larger than n, then what you mean by the k is controlled by this inequality. Is that cool? So you want something like, you know, once k is set, you know this one. Alright. And you know this one gets to be so large. So you know for all epsilon dot to 0, one can pick and that is large enough. So you want epsilon to be larger than, check. You want this one to be larger than n. So that k is lower than epsilon. So you know if this one is epsilon here, so you want this one to be larger than n.
What I thought one plus k to the power n is
Yeah, yeah, that's my, I'm thinking about like, to control this, so that K would be not too large, if you can go like N, and so large that K would be not be large. Let me check.
No, I mean, if you're using this inequality, then, I mean.
Yeah, I know, I'll just erase it.
Yeah,
And so you want, once this one is larger than this
No.
one, so that,
But the problem is you can't use, if you give one plus K.
no, that is just.
No, I mean,
for deducing.
you're giving that a lower bound, but that doesn't help you to control the size of K.
It helps us to control the size of K, why? Once K is larger than that one, so that, I'm controlling N. Even K, I'm controlling N, K is the epsilon here. So you want like K square, you want like 2N minus 1 square, that's larger than K square something. So K square over 1 over 2. Just pick this one, and this one, if we pick N is larger enough, so that this one is the one to pick, and this one, okay, so once you pick something like, N larger than 2 over K square plus 1 epsilon square plus 1. Then you'll get 1 plus epsilon to the N is larger than N. One will get 1 plus epsilon to the N is larger than N. By this one. So you just control on this one, so what you have get is this one. And so, N to the N minus 1, it will be less than epsilon. Something like this. Yeah, I think I'm right. That's one proposition. 但是我们第5题就送分了，我们讲不到，等一下。
没差吧？
是吗？
然后先讲考学。
对，我要先讲考学，我忘记考学了 ，sorry。Proposition if something is converged, something is Cauchy. Anyone has any thoughts on this? Just like, so if something converges, then the PMP is less than epsilon, so dPm would less than 2 epsilon, something like this. So if you pick this one, so the proof is done. Okay, something goes wrong here. But I believe that if you know what is Cauchy, then you can understand this proposition.
Yeah, big proof.
Cool. Do I need a like more clear one? I can do that, but do I have time?
You can sometimes.
Yeah.
好，第5题送分。So there's no like the fifth
把
question.
你把那个定理抠出来就好了，不然整张考卷就。
Let me think about it.
整张考卷。
You can use this theorem, okay? We'll give you like half of the points at least. And if you try that out, you might get like whole point. You can use this theorem. I'll not rephrase that. Okay, so theorem would be the sequence if it is bounded and monotone. Then En converges. Alright. I will not erase this one. You can use this one. Okay, I think I have to answer your question about the bounded one. Sure. So there's a proposition on rooting that says if n is bounded, then you can in R. There exists an prime that is subsequent to an that converges. So once you know like an is bounded, you know an is bounded. So you know that an is in this one for some R big enough. So an lies in this one. This one's compact. So every sequence has every infinite subset should have a leading point. So you just pick that leading point and you can find the subsequence. Find the subsequence. Find the subsequence converge to limit point. Okay. Done. We'll begin the test on 30. Alright, 30. 30. So I think the trick here is you first do this kind of arithmetic and you can find what n after all these things.
第二题，可以说它就是两个收敛。
Yes, but of course you can do like something
可以先
like
prove 第一个，然后再说它是两个收敛数列的相乘。
yeah, that won't work. But if I want you to write something like n epsilon argument, you should do this. That'll be a simple one, right? There is no something like complicated as this one on our test. But again, what we're thinking is right is like so like this one you can think about like this one converges to 1. And so these are just like multiplication of two converged sequence.
Yeah.
And so like this whole variable is like just.
Actually, you can use the proof that we prove. 你可以用就是之前相乘那个证明，然后来证第二个。
Yes, of course. You can just try to find. You just put everything in that. You'll see like how n will be chosen. But again, we will not test you on like that complicated question on n epsilon arguments. But yeah, you should know how all this will work. Because like you need to go through it again when it comes to the limit of functions. It will be another like epsilon delta arguments. And everything repeated because it's like control. Do we have converge the function limits? I think we have it, right?
Let me check about
we have to, we have differentiation, so we must have limits on functions.有什么都讲到？
哦
应该
yes
没有吧？没有吧？好，我们都讲到了。这个是下次的。